Hello AP Physics students. This is the first in a series of videos that's going to help you analyze the data that you took during the circuits activity. So before we start, let's make sure you have your notes in front of you so you can take notes as we go, as well as having your circuits activity in front of you. I'd like you to start by copying down this question: what happens to a charge as it passes through A, a battery, and B, a resistor? And once you wrote it down in your notes, I want you to just take a minute to pause the video and write down your thoughts. Welcome back. So let's talk about what happens to a charge as it goes through a battery. And you want to think about what the function of a battery is, what it actually does to the charge. And here you can think about the analogy I demonstrated for you in class where I took the marble and I lifted it up against gravity and then sent it through the tube for it to roll down. And since I did work against gravity, I gave that marble gravitational potential energy. A battery does a similar thing. It takes charges and it pushes them where they don't want to go, specifically protons, towards the positive terminal of the battery. And here it's giving them electric potential energy. So we say that the charge gains electric potential energy. Now we don't actually measure the potential energy. Instead we measure this by voltage. We attach a voltmeter and we track this by voltage. Voltage, you recall, is just another name for potential difference. That's a change in electric potential energy per charge. And so to use the vocabulary, we say the charge goes through a voltage gain. So what happens when the charge goes through the resistor? Well, if you imagine a charge, and the cursor here shows the charge, here it is going through the battery. Let's say it goes up a voltage gain of 5 volts, and then it goes around here to the resistor. What happens next? Well, we say the charge loses potential energy. Again, we don't actually measure the potential energy. We measure potential energy per charge, which we call voltage. And so to use the vocabulary, we say this charge goes through a voltage drop. So the charge has a voltage gain through a battery, a drop through a resistor. If we think back to our original analogy with potential, we talked about the hiking analogy where every time you think of potential difference, you imagine the mountain. And so if it goes through the battery, where is it going on the mountain? Well, it's going against where it wants to go. By lifting the cooler of food to the top of the mountain, giving it gravitational potential energy, it's going up. So it's a voltage gain. When it comes through the resistor, here it is losing electric potential energy. It's like you letting go of the cooler, it rolls down the mountain, it's coming down, it's dropping. So we call it a voltage drop. So the charge has a voltage gain through the battery, a voltage drop through the resistor. If we go back to the analogy, when I lifted the marble against gravity and released it through the tube, of course when it came through the tube, it lost its electric potential, gravitational potential energy. What became of it? Well, of course, like most things, as it rolls down the incline, it's sped up, so the gravitational potential energy became kinetic energy. Here's where our analogy fails. As the protons go through the circuit, losing their electric potential energy through the resistor, they actually don't pick up speed, they don't gain kinetic energy. In fact, they move at almost a constant speed. And that constant speed is rather slow. It's actually on the order of centimeters per second. So as you're imagining the billions and billions of protons moving through the circuit, you really want to think about a lot of them moving, but they're actually moving quite slowly. If this cursor here shows the flow of the protons that move, kind of drifting along, sometimes going the right way, sometimes back on track and going the wrong way, moving along slowly, 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 bumping into each other, centimeters per second, not fast at all. So a lot of them move, but they don't move very quickly. This seems to violate the law of conservation of energy. If these charges are losing electric potential energy but not gaining kinetic energy, well, where's the energy going? Well, a lot of you should remember that the resistor's job is to transform energy, taking electric potential energy and transforming it into some sort of useful energy. And so the lost electric potential energy transforms directly into whatever energy the resistor produces. And so here we maintain conservation of energy. The charges gain energy going through the battery, they lose energy through the resistor to become whatever the resistor does, like a heating element, the resistors we use in the circuits, rotational kinetic energy for the blades of a fan, sound for a speaker. The resistor is made to change electric potential energy into some other useful form. Let's think about an individual charge. There it is. There's a proton, and it's drifting along at centimeters per second. Now, if there's an open switch in the circuit, and maybe the resistor is a light bulb, when you close that switch, the light bulb turns on almost instantaneously, which is rather strange considering the model I just had you think about, that the charges move around at centimeters per second. And if there are centimeters and centimeters and centimeters of wire here, how come when you close the switch, the light seems to turn on instantaneously, when really it should take a while, a couple seconds, for these protons to move there and get around to that resistor? Well, what's really happening is that we don't just track one proton as it leaves the battery and goes to the resistor. Instead, we think about the protons as being all throughout the circuit. They're already there. They're inside the battery, they're inside the wires, they're inside the resistor. And when the switch is open, the protons are not moving. But as soon as the switch closes, the battery gives a shove. It pushes on this proton, which pushes on the next proton, pushes on the next proton, pushes on the next proton, and pretty soon the information that the switch is closed, that the circuit is complete, travels, and all the protons start to move together. This information actually travels at the speed of light. And so there's almost no delay between you closing the switch or making the final connection and the light bulb turning on or the resistor functioning, whatever it is. And so while the charges individually move at centimeters per second, which is very slowly, the information that the circuit is complete travels at nearly the speed of light, with really no delay. At this point, I want you to go back to your circuits activity and take a look at this circuit. If you haven't already, go ahead and draw this circuit, which is the first circuit you did in the circuits activity, the single resistor circuit. I've just removed the ammeters. And you might want to label delta VB as the voltage across the battery and delta VR the voltage across the resistor. These are some of the first things that you measured, and here you were looking for patterns. It should be immediately obvious that delta VB and delta VR are really very close to each other if you look at the grand scheme of things. So let's generalize that by saying delta VB equals delta VR. Why would this make sense? Well, we go back to the idea of this voltage gain and voltage drop. So imagine a charge here. It's right here at the negative terminal. In terms of the mountain, that's at the bottom of the mountain. It goes up the mountain, gaining, let's say, 5 volts. Now it's at the top of the mountain, and it comes around here to go through the resistor. Once it goes to the resistor, it goes to a voltage drop, and then returns here to the bottom of the mountain. Well, if it has gained 5 volts, I imagine it has to lose 5 volts to come all the way down the mountain. So we'll say that whatever it gains by going through the battery, it has to lose by going through the resistor. The gains have to equal the losses. This really is a statement of conservation of energy. Whatever it gains by going through the battery, it has to lose by going through something else in the circuit, in this case, the resistor. Now, if you look closely at your data, you'll notice that delta VR is always a little bit smaller than delta VB, which means that there are voltage losses or voltage drops somewhere else in the circuit. So think about where else the charges are encountering resistance. Hopefully your mind is turned to the wires themselves. We've calculated the resistance of a wire, R equals rho L over A. And so by Ohm's law, any place there's a resistance, there will also be a voltage drop. So here's what really happens. The charge goes through the battery, let's say it gains 5 volts. It goes through some wires, losing just a little bit of voltage, not a whole lot. It loses the bulk of the voltage here through the resistor, so delta VR is very close to delta VB, and then it goes through just a little bit more wire to go back to start. So it gains here, loses a little bit, loses the bulk of the voltage through the resistor, loses the rest to go back to start. The gains equal the losses. Now let's turn our attention to the currents. You measure the current before the resistor, I1, and the current after the resistor, I2. Looking at your data, it should become immediately obvious that I1 pretty much equals I2. In fact, it should really be exact, with no assumptions made that there's any loss of current. In fact, if there's any fluctuation, it was just a minor fluctuation in the meter. So I1 equals I2. Now, you didn't actually measure this, but you could say that I1 is also the charges coming out of the battery, so we'll call that I total. And so we should be able to say that I1 equals I2 also equals I total. This really is a statement of conservation of charge. And here's where some students get confused as to what the difference is between current and voltage. Let's remind ourselves that voltage is really measuring energy. Energy per charge. And charges gain energy through the battery and lose energy through the resistor. Gains equal losses. But that's not current. Current is a measure of the rate of flow of charge. You're actually tracking how much charge is moving per time. And if we go back to thinking about all those protons moving around together, the rate of flow of charge leaving the battery is the rate of the charges entering the resistor, is the rate of charges exiting the resistor, so all the currents are the same. In other words, we can't lose charges. So it's a statement of conservation of charge. At this point, we're going to introduce one more analogy. So we've had the marble going through the tube, the students in the hallway, the plumbing analogy, and really it all goes back to the hiking analogy, but now we're just going to build on that to make it a ski resort analogy. So we take the hiking analogy and make it some more wintertime activities. And this is going to be the most successful analogy to help you understand what's happening as the charges move through the circuit. For each of these, you may want to pause it and write down what you think is represented in the ski resort analogy, starting with the charges. What would represent charges at the ski resorts? Hopefully you had the idea of people or skiers. So charges move, skiers move. So next, what would represent the wires? And hopefully here you said it was something like the slopes or the trails, right? The skiers move up and down the slopes and trails, the charges move through the wires. What represents the battery? Think about the function of the battery, to lift the protons against their will, to give them electric potential energy, and that of course is the job of the ski lift, lifting the skiers to the top of the mountain and giving them gravitational potential energy. Finally, what offers resistance? And here there's actually a lot of things that do that, so write down some of your ideas. We'll go through some of the best examples. There are all sorts of things that represent resistance. One thing might be trees or obstacles. The skiers have to sort of dodge those as they go down the mountain. That offers resistance. It limits the flow of the skiers. You may have also said the difficulty of the slope. This is a great way of representing resistance. You think about a choice to be made, one slope or another, and where the skiers might go. And a more difficult slope might limit the flow of skiers. Fewer skiers might choose that slope. You might also say the other skiers offer resistance. We originally said that resistance comes from the protons bumping into each other. And so when the skiers come down the mountain, they have to avoid the other skiers. They don't want to bump into each other, and that limits the flow. Another good way to think about resistance is friction. This is particularly good because remember the charges move around the circuit at a constant speed, that's slow centimeters per second. So imagine a skier going up the mountain, taken by the ski lift at a nice constant speed, and then to model it, when they come down the mountain, they should come down at a constant speed as well. Now normally, of course, the skiers speed up coming down the mountain, but here, when I think about the coming down as a constant speed, what would cause that to happen? Well, that would be the friction between the skis and the snow. And so this friction prevents them from picking up speed, modeling this idea that the skiers go at a constant speed around the circuit. Also, it's a good model for friction to represent resistance because when objects rub up against each other, what sort of energy is being produced? Well, that's usually heat. And very often the charges lose energy as heat by going through the resistors. One more thing you might want to think about would be bears. I think that if there were bears on the slope, that might limit the flow of the skiers coming down that slope. This is the end of the first video.